Hello everyone, welcome back to Engineering Mechanics. In earlier sessions we talked about particle equilibrium, a very important topic in engineering statics. If you recall, a particle is a concentrated mass. We can ignore the size and shape of an object, making a particle assumption. Particle assumption is very useful in solving a wide range of problems, as we have seen. Having said that, if you would like to analyze a body closely, if you want to perform a very detailed analysis, then rigid body assumption is not adequate, as you can see. So what we have to do is to consider the body as a whole along with dimensions and size. And when you want to consider a body in such fashion, then we will have to perform a rigid body equilibrium analysis, not a particle equilibrium analysis. So earlier we looked at 2D particle equilibrium. Now we are going to do a 2D rigid body equilibrium, meaning we are going to consider a body with all its dimensions and size. All right? So 2D rigid body equilibrium. We are still in 2D, meaning two-dimensional plane. In particle equilibrium, in case of 2D, we had two equations. Because a particle has no rotation. A particle is represented by a geometrical unit, point. A point has no dimension, so there was no rotation associated with the point. So we had two equations in particle equilibrium. Now we are moving on to 2D rigid body equilibrium, and therefore we will have an additional equation. The additional equation comes from the fact that the rigid body can rotate. So we are going to take a closer look at that in a minute. But before we go and do a closer look, let's talk briefly about rigid body. What is a rigid body? As the name implies, rigid body means a body that does not deform. If you want a formal understanding of rigid body, take any body, say pick up 2 points on the rigid body. Here I have a marker in my hand. Let's pick up 2 points, maybe these two endpoints. Draw a line connecting those two endpoints, and let's say we subject this rigid body, our body, to some loading conditions, such as the way I am pushing this. And if you look at it, this body, under the influence of the forces that I am applying, is not changing its dimension. And that would be a formal definition of a rigid body. A rigid body is a body that does not change its dimension under the influence of the forces that I apply. So with that understanding, we want to move on, but I do want to give a word of caution here. All bodies, when they are subjected to loading conditions, will have some kind of a small internal deformations. Those are very important from an engineering analysis point of view, and you are going to study about that later in a class called strength of materials. But in our context, those small internal deformations do not have any influence on the static equilibrium study. So as far as we are concerned, in this class, we will ignore all those small deformations and we assume rigid body as a body that does not deform. All right? So we understand what is a rigid body assumption. Now, rigid bodies are to be supported. All bodies are to be supported, right? For example, I am supported by this floor. If I am not supported by this floor, I will not be standing here. So all bodies are to be supported, and there are a few popular supports that you are already aware of. Think about a pin joint or a pin support. Well, you see this in your life every day. Every time you open a door or close a door, you are actually using pins. The doors are typically supported by hinges, which are actually pin supports. Not just the doors. Take a scissor like this. The scissor has actually 3 parts, the upper part, the lower part, and this is connected by a pin. So these two parts are connected by a pin support. All right? So there are various supports. Popular support is a pin support, which allows a rotation. All right? There is a roller support. Now, for example, here I have a little metal plate with a screw in it. It is actually used in photo industry for mounting cameras. But here I have a slot, and I have a little screw that you can see, and it can spin, as you can see. So it's like a pin support, but in addition to allowing rotation, the slot allows this body to move along that, which means this is not just a pin support, I call it a roller support, which allows a rotation as well as a movement along this. It doesn't allow you to move in the vertical direction. So this pin support, this roller support will actually create one reaction. Again, we are going to take a closer look at this in a minute. On the other hand, a pin support such as this allows only rotation. It doesn't allow any horizontal movement or a vertical movement, meaning the pin connection will give you two support reactions. Now, when I say reactions, reactions are caused when there is resistance. Reactions are created when the support restricts your movement or the support eliminates a movement. So in this case, in the case of a scissor, the pin support does not allow any motion in X direction or any motion in Y direction. It allows only rotation. That's a pin support. Again, to repeat, the roller support, in this case, the roller allows rotation as well as a horizontal motion, but it does not allow a vertical motion, and that would be a support reaction. So the objective of 2D rigid body equilibrium is to typically calculate the reactions from these supports or sometimes other external forces. And we are going to take a closer look at those problems now. Hello everyone, welcome back. We are going to take a closer look at a problem. Before we do that, a quick review. We talked about rigid body. Rigid body is a body that does not deform. And if you want a better way of explaining, here is an outline of a rigid body. I pick up 2 points on the rigid body, connect them by a line, subject this rigid body to some loading conditions, all right? And then I look at that line, it does not change the dimension. So a rigid body is a body that does not change its dimensions under the influence of forces. Any small internal deformation that takes place is not important from our perspective because it does not have any bearing on the static equilibrium. So that's rigid body, all right? Now, the next step is we briefly talk about the equilibrium conditions. Now, I want to draw your attention to what we talked before. We discussed particle equilibrium, meaning a system that is represented as a concentrated mass, and in those cases, we wrote the equilibrium equations as these. Sum of the forces along x direction equal to 0, and sum of the forces along y direction equal to 0. In other words, we had two equations and we could solve for two unknowns. And we have done some examples and you understand that. Now, we are moving on to rigid body equilibrium. And in rigid body, we are considering not only the mass, but we are also looking into the dimensions. So this rigid body, in theory, will have motion along x-axis, motion along y-axis, and a rotation about z-axis. And therefore, in order for this body to be in equilibrium, we have to make sure sum of all the forces along x and y is equal to 0 as well as the moment. So our equations for a 2D rigid body equilibrium will be sum of the forces along x direction equal to 0, sum of the forces along y direction equal to 0. I'm writing the scalar equations. And then sum of all the moment about a point, for example, O, equal to 0. So we will have three equations in case of two-dimensional rigid body equilibrium problem, meaning we can solve for three unknowns, all right? Lastly, when we look at a rigid body, these rigid bodies are not floating in space. In engineering, in fact, a body just floating in space is of not important. We like to get the bodies interconnected so they can do something useful. So all bodies that we talk about in engineering are somehow connected. So in this case, let's take a look at the supports that we are going to be considering in this subject. All right. So support reactions. All right. Now, I want to recall your attention to what I talked before. I showed you a scissor and I showed how a pin holds these two scissors. This is a pin joint. This pin joint allows only rotation. It does not allow any translation. So if I want to represent that on a diagram, I am going to draw the pin joint like this, meaning I can connect something through a pin here, and the pin joint is connected, represented using this diagram. And as I showed you, it allows rotation, but it does not allow translation. That means there will be two support reactions, and those two reactions are a reaction along X and a reaction along Y. And I really do not know the direction, but in general, I'm going to assume the direction is positive when I do not know. So this pin joint can be replaced by two support reactions like this. For example, if I call this joint or this point as A, I say this is A sub Y and this as A sub X. So the pin joint will be represented by two support reactions. The next support reaction I want to briefly talk about is a roller support. Roller supports are widely used in engineering, meaning your body can actually move along one direction. And a roller support is represented in many different ways, but one way is to show something like a pin joint, but put them on rollers like this, meaning this body allows rotation and also allows a horizontal motion, as you can see. So this can be represented using just one support reaction such as AY. Now, if you want a physical example, I want you to take a closer look at this body. Here I have this pin which can move along the horizontal direction, but it cannot move along the vertical direction, and that's why you are getting this vertical support reaction. All right? So this is a roller support. So let's write this one. This is a pin support. This is a roller support. And there is another popular support I want you to understand is a fixed support. What is a fixed support? Well, basically you fix something like this. You fix it like this, and you cannot move in X direction. You cannot move in Y direction. I cannot rotate about Z. It's fixed. It's like a tree on the ground, which is kind of uprooted, which is fixed, and it cannot move. And that kind of joints or connections are very popular. And sometimes fixed support is also known as a built-in support. And how do I represent the fixed support? Well, a fixed support is represented by a diagram like this, where a beam is stuck into the concrete wall, for example. And this obviously eliminates all motions. Therefore, it will give you three support reactions. And those are support reaction along Y-axis, support reaction along X-axis, and finally, it eliminates the rotation, and that rotation can be represented like M sub A. That's a moment. That's a couple moment. All right? So these are all popular support reactions that I want to make sure you understand. So pin support, roller support, fixed support. In addition, you will also hear about a smooth surface. A smooth surface is like an icy surface, and if you stand on it, obviously the surface supports you because you're not going down, but it doesn't help you in keeping your motion away from X or Y direction. In fact, you can move along, and therefore a smooth support, which can be represented simply a floor like this, and this is a body. And if you want to represent a smooth support, it will be like a roller support. You will have a direction along the vertical axis. All right? If it is a rough support, you could have two support reactions. So a rough support would look something like this. So this is smooth. This is rough. All right? These are all the supports that I want you to keep it in mind. There are numerous other supports. Cables are another support that we discussed a lot. When you are dealing with a cable, there is always tension in the cable. Therefore, you know the line of action of the force all the time. So these are all the popular supports. Now take a look at an example that involves these supports, and we will solve for support reactions. All right. Here is the problem. This problem is taken from the popular Beer and Johnston text, 10th edition. Simple problem. And let's take a closer look at the problem. We have a beam. We have a few applied external loads. And the beam is supported here by a pin joint. And you can recognize the pin here. And this is your ground. And then here, the pin is supported by actually a cable. The cable is tied to something on the ground. Many students confuse this with a pin joint, but basically a cable is tied here. So our interest is only the cable, so we don't even have to worry about the point C. All right? So how do we solve problems like this? Well, the steps are going to be the same, and I want to make sure you completely understand that and follow this every time. When we deal with static equilibrium problems like this, the first step is to draw a free body diagram. You know how to draw a free body diagram, and we must do this properly step by step. A free body diagram is a self-contained mathematical model of a physical system. It has all the information necessary for solving. So we must draw a good free body diagram. You make a mistake in drawing the free body diagram, your equations will be wrong. And if your equations are wrong, then obviously you won't have the correct answer. So it's very important you draw a correct free body diagram. After drawing the free body diagram, you will have to develop the equations and then solve them. All right? So recognize the supports here, pin support and a cable support. And we are going to disconnect this body or free this body. I want to show you the body. This is the body I'm going to free from the supports. In fact, that's where the word free body comes from. Freeing the body from other bodies or supports. In this case, there is only one body that is connected here, and we are going to free it from the support. And then we are going to draw a free body diagram. All right? So here is my body again, or the system again, in a smaller diagram, and I'm going to draw the free body diagram. So here is the free body diagram. I'm going to draw it right here on the side, on the right-hand side. And this is my point A, and this is my point B. I have not drawn this to scale, but it is going to represent the free body of this beam. So, as I told you, pin support here, therefore it will have two support reactions, and those two support reactions are going to be A sub y along vertical direction and A sub x along horizontal direction. This is the two support reactions from this pin. There is also support reaction from the cable, and you already know the cable is always on tension. So if I disconnect the cable here, the tension will be on this direction, and that's my cable tension, and I'm going to call it T because it is my tension. So these are all the three support reactions. And remember, in 2D rigid body equilibrium problems, there are three equations. Some are the forces along xy equal to 0 and moment about a point is equal to 0. So there are three equations. And if you look at it, we do have three unknowns. So you should feel good that we can solve this problem in theory already. Now, what else is not shown here? We have shown the free body, and we have to now show all the forces. I have shown the support reactions, which are the forces. That's the first step. Then I want to show all the external loads that are shown here. So I'm going to start here. This is my 15-pound force. Here is my 20-pound force. Here is my 35-pound force. Then I have my 20-pound force. And then I have my 15-pound force. So I have freed the body. I have shown the support reactions. I have shown all the external loads. All the forces are shown and labeled, and my critical dimensions are right here. And the only thing that I have not shown is a coordinate system. So I'm going to say my coordinate system is going to be this, x, y. All right? Now, that's a complete free body diagram. And with that information, I can move on to the next step. Strictly speaking, I should show these dimensions here. So I'm going to just put that in here. 6 inches, 8 inches, 8 inches, 6 inches. Now, this is a complete free body diagram, everybody. Understand that. Once I have the free body diagram, I never have to look back anything else. A free body diagram must be self-contained, and I believe I have all the information necessary right here. All right? So now the next step is developing the equation. So let's start with our traditional approach. Sum of the forces along x direction must be equal to 0. So if I look up, I have no force other than a sub x along x, and therefore a sub x equal to 0. That's my first equation, and that is also part of the answer, because the question is finding the support reaction. So I got this one. Now I'm going to sum of the forces along y direction equal to 0. So I start with this negative 15. Realize these are all negative direction. Negative 15, negative 20, negative 35, negative 20, negative 15, all these applied loads. Then I'm going to also have support reaction positive AY and a negative T equal to 0. I can reorganize this, and if I reorganize this, it is going to be AY minus T. I'm keeping unknowns on the left-hand side and the known constant to the right-hand side. And if you add up all this, 15, 20, 35, 70, 90, 105, this is my second equation. It has got 2 unknowns. So I cannot solve it. So I'm going to go to the next step. All right. The next step is, the easiest thing would be to take a moment about any of these points. And I am going to take, say, for example, moment about point B. If I take moment about point B, I won't have any moment due to the force T, tension, because there is no moment arm. I'll be able to calculate all other moments. And since there is only one unknown, I will be able to find out A sub y immediately. On the other hand, some of you say that I'm going to take moment about point A. That would be fine as well, in which case you will be finding the T first. So let's take moment about point B should be equal to 0. And if I did that, I'm going to start in one end and keep going, so I'm not going to miss any forces in the process. So 15-pound force gives you a counterclockwise moment. As you can see, it is going to go counterclockwise. So it is 15 pounds times this distance. From here all the way, that will be this distance, 6 plus 8 plus 8 plus 6. That would be 8, 8, 16, 28 inches. All right. Then I'm going to move on to the next force, 20-pound force. Again, that is going to give you a counterclockwise moment. So plus 20 times this distance, 8, 8, 16 plus 6, 22 plus 35, which is going to give me a counterclockwise moment as well, which will be equal to 35 times 14 plus 20, next force, times 6, and I'm going to continue in the next line. I'm done with all these forces. Now this 15 pounds force won't give any moment because it is right here. T won't give any moment. So the only force that, and AX obviously won't give any moment. So the last unknown support reaction left in this particular equation will be AY, which is actually going to give you a clockwise moment. Why? It's directed upwards. So it's going to be negative AY times 6 equal to 0. Now, I'm not going to spend time expanding right now here. You can do this yourself with a calculator. If I did that, I'm going to calculate AY right away, and it is going to be equal to, if you did your math, 245 pounds. So this equation, moment equation, immediately gives me the answer for this unknown support reaction. So with this information, now I can go back. This is my third equation actually. And I can go back and substitute this, and I can find the tension as, if I substitute the 245 here, my tension will be 140 pounds. And if you have done this correctly, so I have my free body diagram, I have my equations, and the final answer I would give it like this. A sub x is equal to 0. A sub y is equal to 245 pounds, and the direction is this. Finally, tension is equal to 140 pounds, and it is going to be in this direction. And here is my answer. So I have solved a simple beam problem involving 3 support reactions. And that's all we have to do about this problem. And let's move on to the next example.